I'm starting the live stream. Hello, this is going to be Chill Maths on Twitch. I'm James, and today, like most days on Chill Maths, I am reading about quadratic forms. I don't know if anyone's joining at the start here, so it might just be me. And I am going to be learning about values that quadratic forms can take, which is the new thing that we're doing with quadratic forms. Hello, Maths22222. Good to see you. Hello, everyone. I think it might just be the two of us today. There's other things going on. I was listening to Radio 5 just now. There's rugby on, there's cricket on, there's tennis on, there's also the British Grand Prix on. And to be honest, I've got the leaderboard for the British Grand Prix on my other screen, just in case. Hello, EmiFly12. Am I going EmiFly12 or EmiFly12? Hello, nice to see you. First time in chat. Good to meet you. Or good to maybe we've met before. What do I know? Good to see you, EmiFly. I'm gonna go. Yeah, possibly. I can make a syllable out of the middle, but I'm gonna go EmiFly12. And hi, Mary as well. No ads this time. Ah, right, of course. I just am like intro at the start, but no one hears it because of the ads. Good to see you. Right, Maths222 is doing a long message. Interesting. Thanks for the build up as well. I'm excited now. Right. Okay. Good. You right. Okay. What do I think this says? I'm gonna have to copy that out, aren't I? This looks like a proof that there's a prime between n and 2n or something. Maybe. Let's write it out. Okay, that is a long message. We can do. Oh yeah. It is about primes. Good. I can recognise maths. I will engage with that maths in a second. But Mary has noticed the T-shirt arrived. I've got the T-shirt. The T-shirt's happened. We did the thing. RFL. We did it. Also, I now declare the T-shirt. It arrived. It worked. It came with like loads of paperwork because it's been imported from a different country, from my point of view. But introducing new chat commands for people who have just joined. This is going to look weird, but a few months ago we designed a T-shirt. I can explain it in a second if you like. It's got loads of pie charts on, arranged in an intriguing pattern. I got the cheapest option for T-shirt fabric, and it feels just like a kind of maths T-shirt. If you buy a maths T-shirt online and it comes and it's got maths on it, but it's kind of quite cheap, then that's what it's like. If somebody's giving you a free T-shirt with maths on, that's the sort of T-shirt we're like. Oh, and I don't know about the hoodie dress. I haven't tried the hoodie dress. I've only tried the T-shirt. Oh, that's not true. I've tried the T-shirt, and I also couldn't help it because I love them so much, I have a sticker of it as well. Of the design that we made. I haven't decided what I'm going to stick it on, but I'm really excited about this because it comes in. Can you see this if I hold it up? You can see my face through it, right? It comes in a variety where the background's transparent. I made a PNG, so the background's transparent, so it will be just the pie charts. I can stick it on anything. It doesn't have like a background to it. I don't know. I'm going to put it on my water bottle or something, and then the background will be water bottle. Hello, Herb. Good to see you. Right, introducing a new chat command as well, which is !T-shirt. If you type !T-shirt in chat, then this Streamlabs bot tells you what T-shirt I'm wearing. I'm very pleased I've set this up. Yeah, it uses clever technology to scan the live stream and work out which T-shirt. Not really. And it has no. Yeah. And there's a Bitly link so that if you want to, you can also get a copy of the T-shirt. Seen here being worn by some models. Headless models, what's happened there? Okay. Their identity has been preserved. You can have it on any colour. I've gone for black, but because of PNG technology, they'll make it work. I don't know, well, what's that? Graphite heather. That one looks all right as well. And if you scroll down, there are other products. I think if you click through the other products, men, women, stickers. Ah, yes, the 3 genders. You can grab a sticker. Or is this where I find the hoodie dress? I can't remember if I've still got the hoodie dress in the. Anyway, never mind. Good, right. I made a shirt. I'm very pleased. I'm very pleased with myself. The story here is that I wanted to wear this T-shirt, and it's not that much work for me to set it up as a website page where you can also wear this T-shirt if you want to. Right. Any proceeds from the T-shirt go to the Sutton Trust, just like any proceeds from this live stream, if it ever makes any proceeds. Sorry about all the ads. If it ever makes any proceeds, go to the Sutton Trust. I've been offline for a bit. The ability to wear. All right. Okay. Unlock. Right. Okay. Where am I going to go? I'm going to go. Let's put a blank page in, or something. No, let's just go to the site. Let's try and do this in a margin, because I did see. We're down there somewhere, but I did see. That's as much as I can do. What is this thing going on? I feel a bit sorry for Imifly12, who joined chat, and then immediately the maths thing turned into like this real corporate, like I started trying to sell stuff to you. It's not normally like this. I don't normally sell things. I'm not certain I'm selling anything now. So what have you got? You've been told in chat, what am I reading? That this is less than log 2. We're halfway through some sort of argument. Well, maths 22222 is. And they have seen this much maths, and then repeatedly add. That's what they've been told to do. Repeatedly add. And they're supposed to substitute it, with, instead of x over 2 to the k. So that'll be a big sum where things will keep cancelling on the left until you get down to x over 2 to the enormous number. And then you're supposed to get, so there's a calculation here to add together lots of logarithm sort of things. You're supposed to get 2 log 2x, which, do I believe that? I'm not sure. Plus, and then there's this order log squared x that I don't understand. That's the chat message from Maths 22222. I think we should check the logic works. It's not obvious to me that the logic works. This idea that you can add these things together. So we have psi of x. I think I see what's going to happen, but let's work it out. So I think it's psi of x minus psi of x over 2. And then we'll have another one like this. And then we'll have another one like this. And I think they want us to keep adding, possibly forever, or possibly until we get down to psi of something that's less than 1. I'm going to write that as 2 alpha and psi of alpha, where alpha is less than 1. Maybe you have some boundary condition, like if the number is small enough, then this thing will be smalled. I can't remember. I don't know anything else about psi, so there you go. Right. So I don't know this boundary condition. Right. Okay, it's gonna be 0. That's good news. That's kind of what I wanted it to be. Cool. Right. I think I haven't seen the context, but I think this is something to do with the number of primes or something. So okay. And this is going to be using the fact that we've got. This is going to be less than log 2x, log 2x over 2, log 2x over 4, because we're using this fact again and again and again with different values, sort of different values of x or different expressions substituted instead of x. And then this is going to be x over, So what do I write here? Oh, I write 2 alpha, I suppose, but there's something unsatisfying here. And there's these remainder terms, which I'm going to write out like this. So I think adding these together, I'm pretty confident that that's going to be about 2, what is it, x plus x over 2 plus x over 4 plus, if x is large or something, or to a good approximation, this is going to be, this is very, very small on the end, so we're just adding up more and more of these until we get roughly 2x, which is something I can see over here. So I sort of believe that. Formally, I should probably think about how close we are to the number 2, because if you add up finitely many of these fractions like this, then you don't quite get 2x. But park that for a second, because the thing that makes me think about, I think the question that you want to know is, where's this log squared come from? And the place I want to look is, how many of these lines are there? you're proposing to add them all together, and I think there could be quite a lot of them. You're halving each time, and you want to keep going until you get to something that's about 1. Alpha is less than 1, but 2 alpha is greater than 1, I think, is your kind of stop condition. There you go. There are quite a lot of them. You've been halving quite a lot. How many times have you had to halve? Something to do with log base 2 of your number. So there's quite a lot of lines here, which tells me I think that these order log x errors, there are also log x many of them, so they could all add up. Worst case scenario, they could all add up to be log x squared large. That's, I think, what's going on. Yeah, there you go. There are roughly log x of them. It also gives you a handle on how close this is to the number 2, but I don't think it matters very much because the difference is going to be very, very small. Like the difference for this geometric sum is between this sum and 2 is about the same size as the last term. It's multiplied by log 2, fine, but this last thing is sort of order 1 quantity for how different you are from 2x log x, which is really, really small, much smaller than log squared x. There you go. Okay, cool. I think that's it. Is this a proof, by the way, that you? What does this do? No, I don't know. This is like the middle step of some maths. Sometimes I help with other people's maths, and sometimes I try to do that, but it doesn't work. Good. What else have I missed in chat? People. Herb is here, which is fantastic. Good to see you again, Herb. Mary is here. Have I said hi to Mary? Hello, Mary. Yes, good. Okay. Bit of chaos. I've got the Formula 1 leaderboard on a different screen. If you're playing along, then Hulkenberg has just passed Stroll, which is not normally notable, except in this race. That's currently the battle for 3rd somehow. So, normally that would be the battle for 13th or something, but due to hijinks in the race so far, they're all back on intermediate class, of course, good. That's the battle for 3rd at the moment. So I've got that on in the corner of my eye, just to see if that will continue to be a thing, or whether Hamilton will come and grab a podium, which is also something I would like. F1's so good. F1 is so good. This race in particular has been very fun. Hamilton has passed Stroll as well. Stroll's dropping through the field. Right, it's now Hamilton in a Ferrari versus Hulkenberg in not a Ferrari. We haven't exactly seen this battle before, but I sort of think it might go the way of the impartial British observer. If there's such a thing as an impartial British observer, I'm not sure. Also, Lando's getting the win because of a 10-second penalty that I don't understand, but whatever. Neutrino's probably watching this, yeah. I've just got the numbers. I haven't got like TV feed or something. You don't need the TV feed. It's a sport you can enjoy just through numbers. Right, okay. Ooh, that maths that we were doing was a Ramanujan proof. Ooh, okay. Have you got a link to that, or is it in a book? I'm probably not going to do it. We're probably not going to read through the rest of it on stream, but I might try and find it off stream if you've got a link. Right, moving on though. Previously on the stream, we were looking at the values that quadratic forms can take, and I've had a really nice experience this week, which I'd like to tell you about. Is this kind of evidence that doing number theory has actually lined up with some questions I care about. So I had a work experience student in this week, and she was doing an activity, which was testing activities for us, and she was doing an activity where we noticed that 36 is a square number and a triangular number. It's a square number because it's you can write it as y squared. Has an integer solution, and you can also write it as x times x plus 1 divided by 2. That's the formula for triangle numbers. So different values of x and y, but you can write this out as a kind of equation for x and y. So we talked about that bit, and I realised that this is the sort of number theory that maybe I know now, because I've heard of this problem. There's a mathematician. Where are you based? Let's try and get your site. Yes, so there's a mathematician, Beth Romano. Romano. Come on, James. It's not that different from the word Monroe. I can spell Romano. Who's at KCL in London. And I know Beth does a number theory taster talk, which is all about numbers that are square numbers and triangular numbers. I know that because I've seen the title slide, but then I wasn't in the talk. So I remembered, based on that experience, let's keep that. Based on that experience, that I should be able to do some number theory on this, right? It's a classic number theory puzzle. So what do? Well, if you rearrange this, you can make it look like a quadratic form. Let me show you how. So if we double everything to get 2y squared, and I'll move everything onto the right. Do I want it on the right? Yeah, let's move on the right. So double everything. That's already looking quite good because our quadratic forms look like x squared and y squared, maybe an xy term in the middle. It's not quite there because of this plus x thing going on, but we can complete the square. So rewrite this as x plus a half squared minus a quarter. And if I now multiply this all by, did I already double? Yeah, if I now multiply this all by 4 and bring the quarter on the other side, I'll get 1 is equal to 2x plus 1 squared minus 2 times 2y squared. So what we need is an odd value of this, odd value inside these brackets, and an even number inside these brackets, but that satisfies u squared minus 2v squared is equal to 1. We're interested in integer pairs u and v, such that this quadratic form on the left takes the value 1, and that's exactly what we've been doing on Chill Maths. So yeah, this was really good fun because we had this thing came up in my normal job that I was talking to a teenager about numbers, and helped by remembering that this is an appropriate level of question that you can mess around with, fiddled around with it until it turned into this problem, which we have solutions for. So then at work I loaded up Maths 222's Desmos thing, which plots all of the solution or all of the values of this quadratic form. So it takes any quadratic form. This is a really good tool. It takes any quadratic form and shows you the values. By doing Chill Maths on Sundays, we now know that as well as taking the value 1 in the obvious place when x is 1 and y equals 0, it takes 1 in these other places as well. And if you zoom in, there's a periodic line that goes over here. Let's label this to a bit more depth. There we go. So we can sort of keep going. I'll mark in some boundaries. And you can keep finding these points further and further in. So that's 17 over 12. Keep finding these points over here where the fractions x over y converge to root 2. And the pair of numbers always has u squared minus 2v squared is equal to 1. And because of mod 4 stuff about square numbers, it's always the case that you have odd square minus even square if you want to get 1 as the answer. So it always lines up perfectly. In other words, the things we've been doing for approximations to the square root of 2 and the separated line of the topograph of the fairy diagram, all working together gives us pairs like this, 17 over 12, which satisfies this equation, which you can then turn into a number that is both a square number and a triangle number. It's so good. Okay. So working backwards, we get solutions from our understanding of the topograph of the fairy diagram, like this one. And there's more. And we've got a formula for generating them by moving along the separator line. It's periodic, so it keeps stepping along. And working backwards, I then go 2x plus 1 is 17. So x is 8. 2y is 12, so y equals 6. So I get back to the square number gives the square number 36, which is also 8 times 9 over 2. But we can go to the next one if we want to. The next one, I think, is 99 squared minus 2 times 70 squared. And that gives x is 99 take 1 is 98 divided by 2 is 49. Y equals 35. which gives some humongous number, 49 squared. Can I do that in my head? I don't think I can. I also think I've made a mistake by not dividing by 2. No, I have divided by 2. No, 35 squared. 35 squared, not 49 squared. Which I can do is 125. So it's this number, which is 49 times 50 divided by 2, but it's also 35 squared. And you can keep going, because we know this line is periodic. And you generate here, for the values of u and v, you get approximations to root 2 if you take the ratio. But if you plug them in and do this transform to them, 2x plus 1 and 2y, then you get solutions for this question about which numbers are square numbers and triangle numbers. Really good fun. So this is a bit of like my normal life, where having done number theory almost every Sunday for 6 months has been actually good for me. RFL. Sorry, RFL is what we say when we're celebrating a win, because it lined up with what I wanted to know. Yeah, we have an emote for it. Lined up with what I wanted. It gives me hope that maybe doing more of this book, because look, halfway in, doing more of this book might help me understand more things that I have questions about. Like, on the t-shirt, there's this question about, along this vertical line, which is not the first one, the second one, nobody knows if there are infinitely many filled in pie charts, just single colour pie charts in that column. Nobody knows. I can see down the bottom, I've got, let's demonstrate here, down the bottom, so this one working up red, orange, yellow, a kind of lime colour. Those are Gaussian primes on that column. Nobody knows if that keeps going forever, that you keep getting Gaussian primes there. Seems likely, but that's primes of the form n squared plus 1. This is where you have to check if questions are appropriate or not, or think a little bit about, is this a thing, try and look it up or try and remember, does this precisely fit into a class of problems that I've solved? Because there are similar questions that are just really hard and unsolved. So you have to be careful not to try and apply things where they don't work. Right, F1 update, nothing's changed. It's all just exactly how it was. Sometimes this sport is not. They just go round and round. They just go round and round. Oh dear. Right, okay, that was a nice experience. Nice experience. Not going round and round, repeating myself, but being able to fill in the details. That's what I like, because I was vaguely aware this was a kind of Pell's-Lagrangian number theory thing, and I'd seen a bunch of stuff, but being able to piece it all together myself felt really nice. Happy. I'll drink some tea. Right, somebody has started doing something like hoovering or possibly trimming a hedge. Sorry if that's coming through. I can't find an online copy of the book. Well, I kind of just wanted to read the rest of the proof that you were reading. Maybe I'll look it up. Or if you've got the name of the book, I might have access to it, or be able to find it. Yeah, okay. Don't post maths, because it's hard to type maths, unless you want to. But if you've got like the name of the book or something, that might be enough. Mild noise for you, quite loud for me. Well, maybe they'll finish in a second. Okay, right. Motivated by being able to explain triangle numbers to teenagers, let us look at this representation problem. Here we are. Right, and we've had some maths to talk about representing coprime numbers, haven't we? Because where are we? Are we behind this or are we ahead of this? Yeah, there was this sequence of propositions that we went through quite quickly. Yes, thank you. Sieve methods is something I want to understand, because I think some of the researchers in Oxford use sieve methods, and I don't really know what they are, but I got one of them to explain a bit to me. The thing she said was that you could make a set where, so imagine you had a machine that told you whether or not a set contained infinitely many semi-primes. Then you might think such a machine is quite useless, because semi-primes, things that are the product of two primes, such a machine might be a bit useless, because it's not telling you about primes, the things we care about, it's telling you about semi-primes. But if it's a machine you can point at any set of numbers, you're trying to do something like Dirichlet's theorem. You're looking at a list of numbers to find out, does this contain infinitely many primes? And somebody's built a machine that detects whether it has infinitely many semi-primes. You can be clever with your choice of set. For example, you could point such a machine at the set made of numbers of the form p times p plus 2 for primes p. And if that finds infinitely many semi-primes, then you've found infinitely many twin primes. So sort of even a machine that can only detect semi-primes could be applied in clever ways. And I don't quite know what the machine is or how any of this would work. And I think actually because that's an open problem, so maybe we don't have such a machine or something. But if we had technology like this, then we could apply it intelligently to do interesting things. Right. Okay. Okay, so we have this string of propositions. Oh, I'd like to do this. Yeah, we had there's a lot of parties around here at the moment. People do summer in a big way in some houses around this place, which is fair enough. It's been quite nice. F1, everyone's pissing. That's exciting. I imagine that'll be great fun for all the mechanics. They're all in the pit. They're all popping in the pits, except for the lead McLarens. That's very interesting. Right, let's not get distracted by Formula One. We could, they can. They've only got 10 laps to go. They've only got 10 laps to go. The McLarens are going to try and hang it around the lap ahead. That's fantastic. Hulkenberg still third. Still amazing. Sorry. Right, okay. We had this whole string of propositions last time. Divisors can be represented. Why was that true? Yes, because if you could do this, then we thought about it, and you could split it up and do a different form. Different looking form with the same discriminant. Yes, represented in discriminant delta. Doesn't mean by the same quadratic form, it means by a quadratic form with the same discriminant. Bit disappointing. For the ones I care about though, there's a unique thing going on there. Okay. Right. Represents n, even only if delta is congruent to square mod n, and that's come from the discriminant. It was very exciting because this is the moment where everything turned into quadratic residues. The question of knowing whether or not this thing is a square mod something is quadratic residues, which we've seen in different contexts. It's a bit like asking what digits can a square number end in base 10. It's not all of them. You can't have a square that ends in 7. That's the quadratic residue for base 10. Did you? Can I have a link? I'm not going to say no. Authorized online. Thank you very much. Cheers. Reading list. Oh, brilliant. Look. Reading a maths book, being linked to maths books. 20,000 views. Wow. 2 eyes emoji. This is popular Civ theory book. Right, good. Okay, good. Thank you very much. I'll look. Okay. So we had 6.2, and then we had 6. Yeah, so then we're looking at which numbers you can actually do. Because we know that it's 0, 1, the discriminant is always 0 or 1 mod 4, and then the question is which ones of those are actually squares. So let's look in there. And then there's some Chinese remainder theorem thing down here, maybe? If 2 coprime numbers are both represented, then so is their product, and this is about finding a square root or something. So proof of... yeah, we're going to need this lemma first. If a number is square mod m1 and also square mod m2, then you're good. Off you go. Is that right? Yeah, you've got to solve a pair of congruences. You've got to find something that's congruent to the square root mod m1 and the first square root mod m1 and the second square root mod m2. And you can do that mod m1, m2. And then 6.3, you need this odd restriction in here as well. And I found this quite hard last time. This time I'm just going to skim past it. It's okay for things to be hard. Oh, look, a little ice cube. That was going to be an emote or something, wasn't it? Who knows? I'd forgotten we drew that. Oh yeah, a little emote. A little ice cube. Yeah. Okay. And then there's this slightly wonky thing where 2 is a special case, talking about whether x is a square, is it a quadratic residue? X is a square mod p to the r for each r greater than 1. You go up to higher powers of p. 7 cubed is 343. Square mod 343, since 2 is 108 squared, 343. And the proof of this is not quite constructive or something, is it? It's to say, oh no, it is. It's to say we want all of this to happen. Tricky. Where did we get with this? No, yeah, sorry. Forgot about it. Can I make a memo or something? Just look at this. A bit of paper that says make a t-shirt. There we go. We need more emotes. We have slots for emotes. They've increased the number of slots that I had, and I wasn't using all of them anyway. More emotes. Equivalent to p defining r minus 2k. What was this proof? So this was last week as well. I've got half an hour of stories and recap, but here we are. What is this? Good question. How many slots are there? Let's have a look. Emotes. What have we got? Oh, maybe not as many as I thought. So standard emotes on the free tier, I've got 1 open slot. And then at tier 1, if anybody subscribes, I've got all 5 open slots, plus a couple more animations. We've got some animated emotes, the kind of multicoloured RFL thing. But we've got 1 open slot at the free level, which could be the Ice Cube, I suppose. Emotes, very important. Everyone loves emotes. Hello, Fogle Stream. How you doing? Good to see you. Talking of emotes, look at this little rabbit character. What is this? It's a little cat. Focus24 Drum Cat is watching. There you go. It's one of yours. Right. Okay. Fogle Stream is very good at Twitch. What are you streaming at the moment, Fogle Stream? Last time I tuned in, you were doing some coding, although I can't remember what you were coding. To learn. Tree studies and data science. When I saw tree studies, I thought biology, and then I remembered that trees are a thing in computer science. Nice. Okay, cool. You can promote your stream in chat if you like. I don't know how to do that, so if you want to tell people when you're live. Wait, no, it is trees. It's tree studies, unless that's a very specific data science term. Wait, oh, okay. Just learning about trees. Good. You've got to learn about trees. Stream. Tree stream. What would I call it? If I was giving that a cheesy name, I would give the stream a cheesy name, like tree stream. Chill trees. Right, now hang on, that's going to sound... Anyway, right. Panic. Kittens and trees. There you go. Good. Right, we were looking at this proof because I want to understand why x is a quadratic residue moduli p to the r plus 1, given that it's a quadratic residue mod p to the r or something. So x is... We'd like to find a number. So we're going to start by looking for something that is, oh, my goodness, it's a mess, isn't it? We've got x's and y's and z's. X is a square mod p to the r, which means it's y squared for some y, mod p to the r. In other words, it divides this, so you can write that out like that if you like. And then we're going to cleverly modify this by keeping the same sort of thing mod p to the r, so that it's got the same square mod p to the r. That's a good start. But we're going to add on some multiple of p to the r to our potential square root, looking mod, next one up, p to the r plus 1, looking for which value of k we should take, so that this thing is a multiple of, overall, is a multiple of p to the r plus 1, so that we get a square mod p to the r plus 1. With me? Wow, what a lot of words. But this rearranges, you can do a lot of stuff here. So you get something that's very nearly just fine, except for this L minus 2ky. Yeah, which this bit's fine. But we want another factor of p in this bit over here. Rewriting this, what we want is this. We want to find some integer k and q that does this, given y and p, and then you're fine. Just go and do it. Because 2y and p are coprime. 2y and p are coprime if p is odd. Y can't be a multiple of p because then it would be 0 mod p to the anything, and it would square to 0, but it's supposed to square to x. I think x is supposed to be coprime. Oh my goodness, working forwards and backwards. We're back over here. Odd prime p, not dividing x. There you go. They're coprime. Oh, back at the start. Back at the start of the lemma. Right, jumping down again. So once you choose that particular value of k and q, whatever, you get a multiple of p in here. And then overall, this difference is a multiple of p to the r plus 1 from another. Squeeze another one out of this bracket. Squeeze another factor of p out of the lemma. We're really trying to find extra factors of p. And that'll give you a square modulo p to the r plus 1. Right, good. Okay. When p equals 2, this argument breaks down at the last step. And you have to do something a bit more subtle, but I'm okay with that. Good. 2 laps to go. Is this Hulkenberg's first podium? Is that what we're seeing? Are we seeing a Hulkenberg's first podium? Like this? In a Sauber? This is nuts. 2 laps to go. Hamilton's in 4th, almost 6 seconds back. I think he's got it. This is amazing. Right, good. Okay. Everyone's back on slicks. What a race. What an incredible race. And I'm learning maths at the same time. Living the dream. Okay. Yes, we've got to build more of this because we're trying to get to these rules about multiplying numbers together. We want to know which quadratic form represents them out of all of the ones with discriminant delta. So far, our rules have been about is represented by a form of discriminant delta. We've sometimes said is represented by discriminant delta. Here it's all spelled out, which is nice. Okay, we've reached the bookmark. 20 to 5, let's go. Okay, if a prime p not dividing the discriminant delta is represented by a form of discriminant delta, then every power of p is also represented by a form of discriminant delta. So these will be co-prime, and we're going to use previous results, I think. We're going to ask about whether, I'm not looking at the proof on screen, we're going to ask whether you can represent, well, I suppose p first, and then, oh yeah, which way around is it? We're asked whether, to represent this number, it's going to be, yeah, I can't quite see how the mods are going to not line up. The thing we just had was about modulo p to the r plus 1, modulo p to the r plus 2, increasing the number inside the mod. But this is just going to be fixed discriminant. Okay, let's read the proof on screen. That was very short. Oh, a bit upset I didn't think of it. Now, here we go. If p is represented in discriminant delta, then delta is a square mod 4p. Oh, it is there. Oh, I had it wrong, the wrong way around in my head, of course. Right, okay. Delta is a square mod 4p. And now delta is, okay, and then mod p, and now we can just use the lemma. I just had this fact the wrong way around. Mod p, and then you can go up to those. And then 4 is coprime to p to the r, so you can, it's also a square mod. You can put the 4 back on again at the end, combining it together. Since this is always a square mod 4. That's by proposition 6.2. All powers of p are represented in discriminant delta. And 2 is a very special prime. In this case, the representability of 2 implies that delta is a square mod 8, and then you're fine, you just keep going. Because if you get to 8, then you can keep going, is the rule. What on earth is sensation black on? No, I'm reading all of it. which is good of me. Good, right. What a copy pasta. That's a new one for me. Right, okay. And if you're keeping up, I believe the F1 is finishing. They round on the last lap. Final lap now. Hamilton's still 5 seconds back on the soft tyres, but 5 seconds back still. Right. Okay. Good. Okay. So for primes not dividing the discriminant, you can build powers. We haven't said how. We haven't said where, which form they're in, but we know that you can. They're represented by some form. You've done a variation. I'm surprised you've done it so sandwichy. A sort of Subway themed variation on an old copy pasta. Right, okay. Now I want a sandwich. Right, okay. Despite the story, which is not nice. Right, okay. Primes that divide discriminant behave differently. Yes, okay, here we are. So proposition 6.7. Primes dividing the discriminant. I think the rule was you can't make powers of those at all. If a prime p divides delta, but not the conductor of delta. I've forgotten what the conductor is. Recall the conductor. Perfect. Then no form of discriminant delta represents p squared or any higher power of p. Each prime dividing the discriminant delta is represented. So p is represented easily with some sort of form like px squared plus qy squared with an appropriate q. So the pq is delta. Plus, or maybe I want minus. Doesn't matter. Try and make the discriminant correct. Oh, divide by 4. Oh, what am I doing? No, it is fine, but I should be careful with the factors of 4. Okay, never mind. Look. The conductor of a discriminant delta is the largest positive number d such that this for some discriminant delta prime. What? Oh, you take out the square, and you're supposed to be left with a number that is either 0 or 1 mod 4. Okay, so then delta prime is square free. Right, okay. What? If a prime p divides delta but not the conductor of delta. So if I want to talk about fundamental discriminants only, ones where you can't take out a square factor and be left with the discriminants, it's not another form multiplied up by m squared. Maybe that's not quite true. Hello, Me Machine Rex in chat. Good to see you. I am on stream, even though Silverstone Grand Prix is on TV and radio and everything, and my second monitor. It's everywhere. It's been a good one, I think. I'm going to have to listen to the replay of that. But first, primes that divide delta, but not the conductor of delta. It's about fundamental discriminants somehow. And the proof of this is long. So here's the start of the proof. Where are we? Down here. Is this going to finish down here? End of the page, down here. Okay. So that much proof. Let's get the statement on screen as well. And let's just try and break this down. You know what we do. It's in different directions. I think the F1 is now finished, and it has finished in quite an exciting way. So that's pretty good. Good day for Williams. Okay day for Williams. They pick up a few points, but I guess bad news for Williams really that everyone else has picked up a load of points as well. Oh, so many points. Oh, right, yeah, I might have to look at the standings as well. Even Alpine have got some points. Kick Sauber, my goodness. Right, okay, enough stalling. Let's look at the proof. Let's close the F1. It's come to that, we're going to close the F1. Enough messing around. Here we are. I thought I could do both at once. Sort of could, sort of couldn't. Distracted Sunday streaming. There you go. Representability of primes dividing delta was the thing we were just talking about. but you can also get it from 6.2. That's one of the initial things about whether or not delta is a square mod for p. For a prime dividing delta, we have delta is 0 mod p. So delta is a square. When p is odd, it follows that delta is also a square mod 4p. Since delta is always a square mod 4. What? Oh, square mod 4 and what? Delta is also a square mod 4p, since delta is always a square mod 4. It's 0, 1 mod 4. I'm being an idiot, but I don't get it. Oh, right, hang on. So delta is a square mod p. We're asked whether delta is a square mod 4p. That's the rule in proposition 6.2 is delta a square modulo 4p, because we're asking whether you can represent p using a form of discriminant delta. And the question in 6.2 that's equivalent to that is asking, is delta a square mod 4p? And the first bit that's easy is to say that delta is a square mod p, because it's 0 mod p and that's a square, and it's also a square mod 4 because discriminants are always 0 or 1 mod 4, and then there's a rule the rule that says you can multiply up using the Chinese remainder theorem. Breathe. Okay. So Chinese remainder theorem in here somewhere to combine together this thing and also this thing. Square mod, yes, underline square mod 4. Good. Okay, combine those together with the Chinese remainder theorem. Woof, 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 woof. Right, buy me machine regs, see you in a minute. Okay, if p is 2, so special case now. Why are we doing p if p is 2? Because we needed to use CRT, we needed these things to be coprime, but if p is 2 and divides delta, then delta is 0 mod 4, because it's even, so it's the 0 mod 4 variety, so it's one of these, so it's one of these mod 8, so delta is a square mod 8, which means that 2 is represented in discriminant delta, so we build it up like that. Both of the options are fine. If you're wondering whether the prime 2 is a value taken by discriminant delta, well, you're just asking whether delta is a square mod 8. And you know that delta is even. So there's not much to check. It's all good. Okay, good. Suppose now that p is a prime dividing delta. Okay. So what have we proved so far? Primes dividing delta. So primes dividing delta are represented. So that's nice. And now we're going to work out whether they're represented by p squared. You're not going to be there for Thursday. That's all right. The stream is recorded, so you can watch that live stream afterwards if you like, or skip that one. It's up to you. Somebody else will have to. Maybe it's me. Maybe I'll talk about ginger biscuits. We have this combo rolling thing where during work, various people will tune into the version of this show that I do that's actually my job, and promote biscuits. Oh, you're going to do it. Mary's going to do it. There you go. Mary can tune into a University of Oxford educational live stream and tell everyone about biscuits. That's just a thing you can do these days. Isn't the internet brilliant? It wasn't an option to do that sort of thing a few years ago. There you go. Teamwork. Bro, right. I'm supposed to be reading about p squared, and we're going to see that p squared is in some sense really easy to represent if you can represent the number 1, because then you can represent any square by just multiplying up your values. Some people don't even count that as representation. They say you have to use coprime numbers. Maybe they only want to talk about fundamental discriminants as well. I don't know. I think in this book we're going to say p squared is kind of easy if you can represent 1. Maybe that's what we're going to say, which is like asking whether, which is always possible. So I sort of think you can always represent p squared. Why would you not be able to represent p squared? Maybe we are not counting the way where you just multiply up. Yeah, okay. Right, let's read on. This form is equivalent to this with p dividing delta, which is this shape. So if you can represent p squared, then you must be able to write it like this, moving around the value wherever it takes p squared. Apply some transformation to the Ferrier diagram, if you like, that moves that region over to the bit on the left, where which corresponds to having the number p squared here ready for the value of x is 1, y is 0. That will always give you a, so in this case after the transformation a must be p squared. Oh my goodness, so p divides delta, so there you go, nice. P must divide b squared. Since p is prime, it must then divide b. So in fact, p squared divides b squared. Good news. So p squared divides delta, interesting. P squared divides delta, which means that it's part of the square part of delta. If you pull out square factors of delta, you will bring out at least one factor of p squared, 2 factors of p, because p squared divides delta. So the kind of square part of delta includes p squared. So p must be part of the conductor. P divides, but not the conductor. So if p does divide the conductor, I think we're all good. Right, yeah, okay. So the thing I was saying about representing the value of p squared, we're actually proving the converse here, I think, that says that we're proving the converse? Not sure what we're doing. I've lost track of which direction we're going in. Reset. We've shown that p squared divides b squared, so p squared divides delta, so p squared divides the conductor. So this is a comment to say that if p divides delta, if you can represent p squared, then you divide the conductor. But the thing we're trying to prove is that if a prime p divides delta but not the conductor, then it can't represent p squared. Is that just the converse? Am I being thick? It's just the converse. I'm being thick. Sorry for the clonk. Hit my wrist on the table. Good. Not good. Right, here we go then. So we've got cases. Why are we doing cases? Right, well, we'll interpret it, and I've got mixed up, so I'm going to keep reading to see if I can get unmixed. Consider first the case p is odd. Then p squared is 1 more than multiple of 4. Yeah, because it's odd. So this thing. Oh dear. Oh dear. Delta is equal to delta prime mod 4. Oh dear, why has that happened? Why has that happened? Oh. Yeah, I don't know why this is delta prime actually. Oh, this is not necessarily the delta prime above. This is not necessarily the delta prime in the definition. Up here, we're not claiming that delta prime is related to this idea about being a conductor. We're just saying there exists some delta prime. We're about to see. This is why I got turned around and confused, because I thought this delta prime was always the one in the definition of the conductor. And we don't actually have any sort of sense of highest value of p yet. Maybe we're about to. At the moment, we just have this. Just delta prime for now, not conductor. It's never going to be the conductor, because the conductor is actually the factor at the front, but we're not doing this conductor thing yet. Oh, notation. Sometimes notation means the same thing as the previous time you saw it, and sometimes it's not quite there yet. Sometimes it's then turns out to be the same as well. I'm babbling. Let's read on. P squared is 1 more 4 because these things Oh no, I'm lost again. Yeah, if p squared is 1 mod 4, then these things would agree mod 4. Because mod 4, you'd be able to divide by p squared. Or multiply by p squared. No, it's fine. Yes, if this is 1 mod 4, then modulo 4, when you multiply them together, it's just delta prime mod 4. I'm getting there. Also a discriminant, because it's you just check mod 4 to see if things are discriminants or not. They have to be 0 or 1. If delta already was, then it was already 0 or 1 mod 4. By the definition of the conductor, p divides the conductor. Good. The conductor could be a larger number though. Thus, if p divides delta but not the conductor, here's the converse, then p squared cannot be represented by any form of discriminant delta. If you can represent p squared, then broadly speaking, p divides too many of the things, too many of the terms in the quadratic form, and your discriminant must have a factor of p squared. Okay. In the case that p equals 2, the assumption that p divides delta, let's look up here again. Well, we're going to go all the way up. So delta is even, and hence so is b. Oh my goodness. Yeah, up here, even number for b squared. Discriminant equation like this now looks like this. So delta is b squared mod 16. Wow, okay. Where's this 2 squared come from? B squared minus 4. Oh, we're thinking about prime squared because we're thinking about whether you can take the value p squared. This is the discriminant's equation for something like this up here, which they haven't written out again, but never mind. Okay. And so delta is b squared mod 16. The only squares of even numbers mod 16 are 0 and 4. Check them all. Wow. Really? Okay, great. Thinking 4, 0, 4, 0, mod 16. Huh. So delta is either 16k or 16k plus 4. In both cases, delta is 4 times the discriminant, so 2 divides the conductor. I'm getting the impression that for the prime 2, you just have to do things manually, and it usually works out to be fine. Or, you start at 8 and then it's fine. Once we know that p squared is not represented in the discriminant delta, then neither is any multiple of p squared by proposition 6.1 because factors are represented, and in particular higher powers of p are not represented. Okay. So in the case of fundamental discriminants, where the conductor is 1, that just means you can't do this then. You can't take the value of p squared. If delta is a fundamental discriminant, then the numbers n greater than 1 that are represented by at least one form of discriminant delta are exactly the numbers that factor as a product like this, each which is represented by some form of discriminant delta with the restriction that you can only have at most 1 for the power of primes that divide delta. That's very nice. That's great. Oh my goodness, look at the next section. Look at the next section. For non-fundamental discriminants, it's more complicated because you can represent p squared if p divides the conductor. Let's reread this, I think. Yes, we don't have the converse. We don't quite have the opposite of this. If prime p divides delta. I said converse before I meant contrapositive. That's very annoying. I've been saying converse a lot. I mean contrapositive every time. Whoops. Now I want the converse. That's how I've noticed. I want the opposite, the other way around. Because now I'm going to start being interested in cases where you maybe can represent p squared. Because your quadratic form is something fun, like p squared x minus p squared y. That can represent p squared. Even though p divides the discriminant, it can represent y squared. That's a quadratic form that can represent p squared. And the discriminant is, oh my goodness, like 4 times p to the 4. Good, right, but it is tea time, as Mary has reminded us by redeeming the tea time reward in in chat, which is a reward for me. It means that I get a cup of tea. Not via the internet, I have to go and make the tea myself. But it's a break for everybody to stop looking at screens for a minute. Maybe think about some maths. Maybe think about where we're going. I'll put this after the break. It looks like we're learning, not for the first time on the stream, maybe not for the last time on stream. After the break, we're learning about quadratic reciprocity. And it's going to be interesting to see how this book handles quadratic reciprocity. Maybe it'll use loads of fairy diagrams and topology. Who knows? This is a thing we're going to see. Ooh, unless n equals 1, the sum of the first n reciprocals is not an integer. Yeah, I'm hoping for topology as well. The sum of the first n reciprocals is not. Okay, so the partial sums of the harmonic series never hit an integer value except for where it starts at 1. 1 plus half plus a third, not an integer. 1 plus half plus a third plus a quarter, not an integer. Proof by contradiction, though. Suppose it is an integer. Multiply up by k factorial if you've got the first k, and then you've got, was that too much? Maybe you've got something very, very even. No, what have you got? You've got something very odd on the left, and you've got something that looks suspiciously even on the right. Possibly. Is that it? You multiply by k factorial if you're something to 1 over k? Something like this. Sorry, I've been nerd sniped. I will go and get the tea in a second. I've been nerd sniped by this fact in chat. Integer kn. And my idea is to multiply by k factorial, which will give me even integer. K is greater than 1. K greater than 1. K is greater than 1, so even integer. Do I know whether these are even or not? I suppose I don't. I was hoping I could just parity this. I'm hoping for an odd number over here. And then a big even number over there. Maybe that works, maybe that doesn't work. In particular, I'm worried about... Yeah, if k is large enough, then yeah, I think this works. No? Oh. Maybe this doesn't work. My idea would be to multiply by k factorial and see what happens. It feels roughly like these are all even, because k factorial is going to include... I suppose if k is 2 or 3, then I'm a bit scared. But otherwise k includes not just the even number in the denominator, but also another even number. That's not true if k is literally 2 though, because then you get this thing. Oh, but that's my last term if k equals 2. So I guess I have a special argument for k equals 2, and then for larger values of k, there are at least another even number. So you're dividing by an individual number, which might be even, but there's at least one more factor of 2 upstairs. So you have all of these different even numbers added together, except for that last one. Oh, that's not 1 though at all, is it? It's k minus 1 factorial. I'm an idiot. This hasn't worked. I thought it'd be 1. Yeah, why is that last time odd? Well, I thought it was 1, but it's actually k minus 1 factorial, so it's nonsense. Right, okay, probably not a good idea. You know when you think it'll be easy, and then you do an easy proof, and then it turns out it must be easy? That's the point, where you go make a cup of tea. Right, I'll be back in a minute and a half, or something like that, fast kettle, with a cup of tea. Until then, you're welcome to make yourself a cup of tea, or just look away from the screen and think about numbers. See you soon for some quadratic reciprocity. Oh, it's a different factor. Oh, no, don't say that. Now I've got to think about that while I make the tea. See you in a minute. Sorry for the slow stop. I think I'm back. I think I'm live. Yeah, so I was catching up with my partner about the Formula One. Hulkenberg podium. First one in, with 239 races. Guys on podium. Very exciting times for Sauber. I'm trying to work out where that puts Sauber in the standings. Because they've been not doing great, but not doing super terribly. Didn't they have a weird... Anyway, welcome back everyone. It's the British Grand Prix has turned out to be amazing. I did not think about the factors at all, really sorry. A factor that's in all but one. After I've multiplied that by k factorial, or no. So after I've multiplied by k factorial, the factor k is in all but one. And oh, can I make k a large prime or something? Is that good? Because then, oh no, I can't control k. K is in all but one, but the other term could be a multiple of k after I've multiplied up. Yeah, so I don't know. Factor, no. Or is it, so you take k and look at all of the other ways you can make k or something. Because that last term was k minus 1 factorial. I still want that to be left out one. Right. Mean Machine Rex says map practice was not easy on Thursday. Sorry about that. We're still interested in areas between curves, aren't we? Oh no, it's your prime thing. I wanted a prime number. I wanted k to be the big prime, and I knew that wasn't allowed, so I stopped thinking. But you're telling me I should choose a large prime a bit less than k, because no, that's in all of the terms, isn't it? Isn't that in all of the terms? Is that in all my terms? Like k minus 1 factorial will include that as well, and then it's everywhere, isn't it? Oh, it's not in the one where it was divided by that prime. It's not in the 1 over that prime term. But it is in all of the others that are missing. Why do I have to take a big prime? Why can't I take a small prime? Oh, because a small prime would have a multiple like 2 times that small prime would be somewhere else. And then there could be some shenanigans cancelling out these fractions. But yeah, okay. So the solution is something like multiply it by k factorial, and now consider the prime between any prime between k over 2 and k, which is a factor of a unique one of the denominators, because there isn't space, because it's between k over 2 and k, there's not space for another multiple of that prime, so it's just in one of those denominators. And because prime, it only divides k factorial once, so that term of the sum is not a multiple of that prime because you divide it. But everything else you can see is a multiple of that prime. Right, okay. Right, so we can use the Bertrand postulate on it, which is the thing you were talking about at the start of the show. Right, good, okay, like it. So I had the right idea to multiply by k factorial, but then I was greedily looking at the last term, which I can only make work if k is a prime. I need a little bit more maths to say it's not a prime, look nearby for a prime around there. A little bit more maths, Bertrand postulate, whatever. Okay, right, welcome back to the stream. Hope everyone's doing all right. We're going to do quadratic reciprocity, which has really beaten me before. The show has tried to learn. Oh, I've really zoomed in. It's getting closer and closer. Quadratic reciprocity has really beaten me before. It's the notation. I just really struggle with the fraction bracket thing. We use brackets for too many things, right? I'm going to try another time. Keep trying. You haven't. No, worth giving up or mumble. Let's go. Okay, so the problem of determining which primes are represented in discriminant, we already know when 2 is represented. Do we? Yeah, because we were just talking about this, weren't we? 2 is represented if delta is a square mod 8, which is always the case. Isn't it? It's always the case that delta is a square mod 8. if delta's 0 or 1 mod 4? No, if it's 0 or 1 mod 4, it might not be a square mod 8. It might be 0, 1, 4 or 5. So then the question is it 0 or 1 or 4 mod 8, but not 5 mod 8? 5 mod 8 would be a problem. If it's 5 mod 8, then the discriminant can be represented by a quadratic form, but it's not a square mod 8. Right, all of that, yes, okay, you look at delta mod 8 and think about squares. Okay, we know primes dividing the discriminants are always represented. Remains are the odd primes not dividing the discriminants, which can be regarded as the generic case. Odd primes not dividing the discriminant. Yeah, please. Okay, great. So all the other primes, we would like to try and build all of them, wouldn't we? I don't think we've done that yet. Yes, that's what we're doing. Okay, so my discriminant delta has got some factors, got some prime factors, but I'm looking at a different prime, and I'd like to know if it takes that value. Good. Okay. Yeah, so here we go then. We're doing the quadratic reciprocity stuff. An odd prime will be represented in the discriminant delta exactly when delta is a square mod p, because if delta is a square mod p, we also know that delta is a square mod 4, and for odd primes p, those are coprime numbers, 4 and p, so we can combine together. And conversely, if delta is a square mod 4p, then it's a square mod p, take the same square root and just mod p instead of mod 4p. If delta is x squared plus some multiple of 4p, then it's also something squared plus a multiple, this is quite clumsy, of p. 4 times as much, but still, it's a square mod p. You might need to reduce, if you like, you can reduce that square root down a bit, mod p instead of mod 4p, but you don't need to. Here's some convenient notation. For p an odd prime, and a an integer not divisible by p. Deep breathing. Okay, p is an odd prime. Good. A is an integer not divisible by p. Okay, define the Legendre symbol. I'm going to pronounce it a over p. I don't really know how other people pronounce it, but I'm going to say a over p. So it's b plus 1 if a is a square mod p, and minus 1 if a is not a square mod p. Right. A over p is 1 if it's a square, minus 1 if it's not a square. A over p. Okay, using this notation, we can say an odd prime p that does not divide delta is represented in discriminant delta if and only if delta of p. Delta is a square mod p. Delta is a square mod p. Delta of p is 1. Positive because it is a square. Delta is a square mod p. That's what we have there. I'm just going to read everything 2 or 3 times because, here we go. We'd like to calculate this because we want to work with these things to work out whether or not, well, I suppose I've got lots of different values of p, different primes that I'm interested in, and I'd like to know whether or not I can make these different primes. I suspect that I can make all of them, the ones where delta is not a multiple of p, primes not dividing delta, primes not dividing a not divisible by p, a not divisible by p, p not a factor of a is delta in that expression down there that we care about. Drink some tea. Right. Is it 3 times or maybe 4 times we've done stuff like this? Never mind. Here we go. So what's going on here then? 4 basic properties make this a feasible task. If you have a product upstairs, so if delta is a product, again, p doesn't divide delta, so p is not going to divide any of this, then the rule is that you multiply these Legendre symbols together. So that's 50-50, isn't it? Because if these are all 1, then I understand it. It says if a is a square mod p and b is a square mod p, then that's fine. AB is a square mod p because you would just multiply those together, and the square roots would be, so if a is x squared mod p and b is x squared mod p, then AB is equal to xy squared mod p. You can just multiply. So one direction, not surprising, but the other direction, the other case, is surprising. And also there's 4 cases here really, because there's 4 possibilities for the brackets on the right hand side. So yeah, so it's not obvious at all that if you can't write A as a square mod P, and you can't write B as a square mod P, that you can write AB as a square mod P. What do you mean complete? And what do you mean minimal? Are you trying to convince me that these are the only properties, or enough to compute all values? Because you can currently see me struggling with what they say. So whether or not they're a complete basis of all facts is obviously beyond me. Yeah, exactly. Can you calculate everything using these? I don't know. I haven't even read them all yet. Give me a chance. Right. Okay. Is -1 a square mod P? And the answer is yes. -1 is a square mod P if P is 1 mod 4, and it's not if P is 3 mod 4. And being a square mod P is very interesting. No, sorry. Being -1 being a square mod P is interesting to me because then this is about we reduced at some point the numbers that could be written like x squared plus y squared to that question, I think, and now I'm just being told that. Are we going to get a proof of this? This would be nice. So and then we're told about 2 mod P. Is 2 over P is 2 a quadratic residue mod P. Yes, it is if P is like this, but no, it's not if P is like that. This doesn't feel like a basis of facts, does it? This feels like some facts. Oh yeah, here we are. If P and Q are distinct odd primes, then it's this, unless they're both congruent to 3 mod 4, in which case there's an extra minus sign, which people sometimes write. And in chat, this has been called odd, but I think I've seen this written like this, right? Let's try and get this right. P minus 3 over 4, Q minus 3 over 4. Is that what people write? No, I need extra minus signs. P minus. Oh my goodness. How did people do this? There's a thing people write over here that does all the minus signs just right, so that if P and Q are both congruent to 3 mod 4, then it spits out an extra minus sign. I can't remember how you write that. It definitely involves brackets multiplied together. What would it be? Do you add them? No. What's this machine? The kind of machinery that people have that does the 3 mod 4 logic for you? It would have to be something like P minus 1 over 2, maybe? Q minus 1 over 2? Because then, if these are both 1 mod 4, then I get okay. Maths 2 in chat agrees, but I'm going to check it slowly. So then, if they're both 1 mod 4, then you get even numbers for both, which is great. You get an even product, and if I do -1 to the power of this big even number, then I get 1. And actually, if either of them is like that, then I get an even number upstairs, so I get 1. That's my final answer. No extra minus signs. But if they're both 3 mod 4, then you subtract 1 and you divide by 2, you get odd numbers. And if they're both odd, this behaves like a kind of AND gate for odd numbers, multiplying things together. If they're both odd, then -1 to that number is -1. So this part of this formula is to do an AND operation to test that they're both 3 mod 4 by converting them to odd numbers and checking that they multiply to give an odd number. And then part of the formula is to spit out a -1. Okay. So this lets you flip things over, and I think you then do something a bit like Euclidean algorithm on numbers, I think. Not sure if you want to actually calculate these. Being able to break things apart is good, if you can factorize something. Right, and then so this is going to say that for a non-prime number up here, you could split it down into its prime factors, and then just think about its prime factors and use rules like this one to flip it over. so that you've got a larger number upstairs, and then use modular arithmetic, because we only care about a modulo p for this symbol. If a is a square mod p, so if a is larger than p, you can do some subtraction, and that reduces it. And that's a bit like the Euclidean algorithm, because then you reduce it, you might get something to split out apart. That's okay. That's smaller numbers, mod p, maybe lots of them, and okay, so induction or something. So then if you do smaller numbers, but then you're good. How do you do any of them? What's the basics case here? So I'd kind of like to know is 1. So 1 always is. 2 we've got a rule for. So you might factorize, or you might just get something like, it's 3. How do you work out if 3 is a quadratic residue mod p for some large number p? Because I can't factorize 3. I don't know what to do. I could flip it over so I get a large number upstairs. This is it. This is the way, I think. Flip it over so you get a large number upstairs, then break it down, and you'll get something like some small thing. Yeah, you need, I think, that rule in chat. Back q minus p. You can subtract multiples of p upstairs, and then I think you're running basically the Euclidean algorithm, but I'm a bit hazy on it. Yeah, let's do that one. Yeah, let's do that one. So this is 78 a quadratic residue mod 97? And my plan here is, well, I don't know, but I can flip it over. Now, quick think, are these both... I should split it apart. Yeah, thank you, good exercise, off we go. So 78 is 2 times 39, 2 times 3 times 13. So the question is 2, is 3, and is, so 6 times, I can do this, 6 times 13. And then my strat for this one, so 2, okay, I don't know about 3 either. But maybe I flip them. Okay, right, there's a 2 over 97, there's a chance for us to use rule 3, which feels more like a fact than a necessary rule, but so maybe I could reduce this one. I'm going to be reducing that one and that one in a second, but let's think about this 2. So 2 is 2 a quadratic residue mod 97. Gosh, and we're supposed to think about 97 mod 8. 97 mod 8 is 1 mod 8. So this thing is this 2 over 97 thing. 2 is a quadratic residue mod 97. I don't know what a square root is, but there's a fact down here that tells me about 2. Okay, 3 over 97. So this thing, I'm allowed to turn it over. Is 97 prime? Interesting. So if 97 is not prime, I'd be in trouble now, wouldn't I? But I'm always talking about having a prime downstairs. So if 97 is not prime down here, then I'm just not allowed to flip it over. And I'm not, I think, not allowed to talk about these things in the first place. These have only been defined for p and not prime. So when I see the question in chat, I have to think, is 97 a prime number? Luckily it is. So the question's well posed, and we're allowed to carry on. Yes, and these ones don't mess with the thing downstairs, so they're okay. Good. Pause to think. So 97 over 3, but both of those things, good, yes, 97 is prime. Panics. 39 flashes before eyes. No, it's fine. Both of these things are... no, so that one's 3 mod 4, and that one's 1 mod 4, so it's fine. I don't need an extra minus sign. And then I can reduce. Because now I can say that this is 1 a quadratic residue mod 3. Yes, it is. And then over here, I'm allowed to flip this one over. 97 over 13. 13 is 1 mod 4, so no bonus minus signs. Now I've got to do 97 divided by 13, which is fun, I suppose. 7 gives me 84. No, 7 gives me 91. Remainder 6. So the question is 6 a quadratic residue mod 13? And I'm going to keep going to the bitter end, so I'm going to write that this is 2 over 13, 3 over 13, and then 2 over 13. I know my 13 is 5 mod 8, so I think it's not. And 3 over 13, I'm allowed to flip that over, and 13 is 1 mod 4, so I don't need a minus sign. And then off we go, we get down to 1 over 3, and 1 is a quadratic residue. So overall, I think 1, 1, minus 1, 1. I think no. I think 78 is not a quadratic residue mod 97. Goodness me. Should we check? Let's check in a stupid way. We haven't done these stupid Desmos for a while. We've done professional good Desmos, which not what we want right now. I want to know all of the squares mod 97. Is that, maybe that's the question. Okay, I've got to get more comfortable with quadratic residues. So I want a list of numbers where list is 1 up to 97. So this should be showing me. Oh, no, I need to show me points like this. There we go. We've seen these shapes before. They look like Space Invaders. They're great fun. This is a map of all of the squares mod 97. So on the x-axis, something to square, and on the y-axis, the square numbers, but mod 97. So they grow, but then 10 squared is down here at 3. So then the question is 78 a quadratic residue mod 97? So if I look at the 78 row, is that 78? No, not quite. There's a gap here at 78. Doesn't hit any of the dots. So some numbers are quadratic residues, some numbers are not. Hooray! We got the right answer. Who knows if we made an even number of minus sign errors, but good, RFL. We made a load of these, didn't we? Because they're good fun. If you change this number to capital N, I think I'm just going to drag these into a sensible order as well. N first. We made loads of these because they're kind of fun. They look like there's several things going on here. So you get this kind of bit where the parabola is relatively what's going on there? There's some symmetry. It's kind of got zero derivative or something. I can't remember what we said last time. Good fun. Looks like a parabola around there, and it looks like a parabola up here. And some of them are different from others. I can't quite remember what we were doing last time, but I think we're about to do it again. So let's keep that around. Okay. Probably 2 will be used when dealing with negative discriminants. Oh, okay. Maybe I do care about this. Various prime factors. Okay, notes underneath. Q squared is always 1. Oh, right, okay. So if you've got some square factors, then obviously Q squared is good. You can make Q squared mod P by squaring a number like Q mod P. Okay, good. Not scared yet. We're good. Probably 3 will be used for certain even discriminants that aren't a multiple of 4. Or are a multiple of 8. They're a multiple of an odd number of power. The power of 2 being odd. Might give us some square stuff, which is fine, and then 2, which might or might not be a quadratic residue. Probably 4 is called quadratic reciprocity. There's a proof in section 6.4 and proofs of everything else in section 6.4. Yep, okay, let's do an example. Is it going to be the one that I just got? Yep. Oh, it's 78 mod 89, so it's pretty close. Good choice in chat, math22222. Maybe go for 78 mod 89 rather than 97, but still. Let's read along. You could list all the squares in Desmos. Yeah. Instead, you can do this using properties. Factor 78 like this, which we just did. Did you know it was 78 on the next page? I don't know. We'll see when we prove them. I think we might be doing some stuff from first principles, and then it's a bit hard to say whether you're using the one about -1 and the one about 2 look different to me. maybe you could be very clever and avoid. I don't know. What do I know? Right, okay, so they're doing something like me, but looking at this, they're flipping this over. After this, we use the fact that p depends on only the value of a mod p, which is a kind of another rule, to reduce this to 2 over 3, and that's to 11 over 13, and then keep flipping. It's probably 3, no, probably 3 is about 2 upstairs. 2 is not a square mod 3, because the squares mod 3 are 0 and 1. Yeah, we should check some of this for numbers like 5, shouldn't we? Is 2 a square mod 5? Well, the rule is to look mod 8 at this number down here, and 5 is plus or minus 3 mod 8, so no, 2 is not a square mod 5. But then, is 4 a square? Yes. Is 3 a square mod 5? Is 3 a square mod 5? Is a question like, is 5 a square mod 3? Because neither of these things are not both 3 mod 4, and they're both prime. Is 5 a square mod 3? It's a bit like asking whether 2 is a square mod 3, and that one is not true because 3 is plus or minus 3 mod 8. What else have I got? Is 1 a square mod 5? Yes, it's the square of 1. Is 0 a square mod 5? Yes, it's the square of 0. And I'm not supposed to have things upstairs like that. 0 upstairs. Okay, good fun. Okay, good times. Not found an actual discovery. Okay. Already seen how to reduce the case of prime moduli. To the case of prime moduli, yes. Chinese remainder theorem, good. The square mod 8 is 0, 1, and 4. So 78 is not a square mod 8, and therefore not mod 88 either, even though it is 1 mod 11. So 78 is a square mod 11. So Chinese remainder theorem does not have this kind of rule that if they're both not squares, then the product. Yeah, the rule for quadratic reciprocity about combining together whether things are squares is very different from the Chinese remainder theorem rule about combining together things that are squares. Because if you have a number that is not a square mod p and not a square mod q, then you can't combine that to make a square mod pq. That would be silly. A square mod pq would be a square mod p and would be a square mod q. But quadratic reciprocity says it's subtly different, but it says if p is a square mod q, then q is a square mod p, unless they're both 3 mod 4. Which is like saying, if p is not a square mod q, and q is not a square mod p. Oh, and the product rule thing as well. Yes, I want to talk about the product rule, not quadratic reciprocity, I think. Focus on that one. If a is not a square mod p, and b is not a square mod p, then the product is a square mod p. There's a group theory proof of that, isn't there? It's something like the numbers other than 0, the numbers form a group. What am I doing here? There's a subgroup for the ones that form the ones that are squares, because the product of ones that are squares is also a square. Half of them are squares, I can't remember why, but half of the numbers are squares. Oh, because x squared equals a has always got 2 solutions. You can factorise them. If p is prime, you're good. So there's always 2 roots for each number, so it's a 2 to 1 function, kind of. So half of the numbers are quadratic residues. And then it's closed under multiplication, so you've got a subgroup there. So then something like, how does that work? The kind of -1 stuff has to fit in, just because if you take something that's in your subgroup and something that's not in your subgroup, the product can't be in your subgroup, otherwise the other one would be as well by inverses. So the product must be -1, like you want it to be. And then finishing off the table, like the multiplication group table, things that are both not squares, the multiplication has to be back in the subgroup because you've run out of targets, but you need all the products to be distinct in your group. Multiplication mod p is a group. There's a fantastic proof that we saw quite a while ago on this stream, to say quite naturally why the behaviour for like is square mod p, if you have like 1 and -1 for the rules on that, there's this good reason why you get this behaviour, which is like multiplying the numbers together. For kind of I'm imagining here a kind of group table for the items. So if you sort them out into ones that are yes, loads of items, and you sort them out here into the ones that are no, then and over here yes and no, everything in the top left corner has to be yes, which means that as a result, kind of Sudoku style, because this thing has to be a Latin square, all the stuff around here off diagonal in these quadrants has to be no, because you've already used in each row, you've already used all the yes items in some order. So then kind of Sudoku rules down in the bottom corner, everything over here has to be yes objects again, because you've already used in each column and each row all of the no objects in some order. So in order to make this a Latin square, you end up with this pattern. It's just so good. There's a subgroup here. You can get, not multiplying by a prime. Not multiplying by a prime. I'm just thinking about multiplying. So if I have like, I'm thinking about this rule where neither A nor B are multiples of P. This kind of rule that you kind of have this yes-no structure going on, but there's a group behavior behind the scenes. The product A and the product AB. It's kind of obvious that the top left corner has to be yes elements. That if A is a square mod P and B is a square mod P, it's A a square mod P, it's B a square mod P. But the product has to be. But then these things are a couple. You can say that every element mod Q is P times a square mod Q. What? What's Q? Every element that isn't square. Oh, right. Yes, actually that's nice. Yes, no, I like that. Yeah. Find some element that's not square and multiply all the squares by that element. Yes, I like that too. Yeah. To get the coset. Good. You know that QA squared is not B squared, else you would have Q is BA squared. And you told me that Q was not a square. Also, the group's abelian, so it's all nice. All very good. Okay, good. In this example, we use the fact that the modulus A9 is prime. Oh, right, blah, 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 blah. Right, returning now to quadratic forms. Yes, please. X squared plus y squared has entered chat. Yes, we love that one. Let's see what the basic properties of Legendre cylinder was. Tell us about which primes represented by some of the forms discussed at the beginning of the chapter. Long sentences. In the first 4 cases, the cluster is 1. Good, easy peasy. So we'll be determining which primes are represented by the given form. That's how I like it. And theorem 6.8 will then say exactly which numbers are represented by this form, confirming the conjectures made above when we look at the table graphs. So good. I think the group has order p minus 1. It's everything except 0 modulo p. P minus 1 is even. I'm proposing to divide it by 2 into ones that are prime and ones that aren't. There's also this lovely test. Are we going to see this at some point? Is this the test? So is a square, is a number a square mod p? Is it Eisenstein's criterion or something? Is that you raise a to the power of p minus 1 over 2. So it's now just something I know, general knowledge, I think. So this has to be either 1 or minus 1. Yeah, here we go. This is the formula for the Legendre symbol, isn't it? In the case. Yeah, okay, we're going to get there, I'm sure. Because this has to be plus or minus 1 by Fermat's Little theorem. Because if I square it, I have to get 1. And there's only 2 possible square roots, mod p. mod p is nice on roots of quadratics. It's all fine. And the rule I think is if this is 1, then it is a square. Yeah, because separately, if a is x squared, then good news, you've got something that must give 1, and also mumbo jumbo, I can't remember, it's exactly half of them, so now you found all of the numbers. It's precisely the ones that give you 1 kind of early. You're doing Fermat's Little theorem, but they've reached the number 1 before you got to a to the p minus 1. So I think we're going to see that formula in a few pages, because I vaguely remember it from a different number theory thing. Hello, Spunk 1, 2, 3, 4, 5, 6, 7, 8. Good to see you. This is number theory. We're learning about quadratic forms, which look like this, and we're learning about which values they can take. Which numbers can you write as the sum of 2 squares? Which is a nice simple question, but we've been learning loads of theory about prime numbers to try and work it out, because the answer is really complicated. The answer is that you can make the prime 2. 1 plus 1 is 2. Welcome to Chill Maths. So the sum of 2 squares. You can make primes that are 1 more than a multiple of 4. You can make any square number, and you can make products of those things. That's the answer. So we're trying to learn the maths for that. Oh, what did I say? Eisenstein's criterion is what I said. What was I supposed to say? Yeah, Eisenstein's criterion is that thing about dividing polynomials. Euler, maybe? Everything is Euler. Let's just say it's Euler. Quadratic residues. Let's see if I can find a thing for... Yeah, not Eisenstein. Can't remember. I think it's going to turn up in a second. I think there's a formula for this. Have I just made this up? No, I've not made this up. It's just fine. It's just fine. Some sort of test? Sure, we've seen it before. Am I getting crazy? Okay, right. Scrolling through a different resource on the other screen. Right, not what you came to see. I wonder if Spunk 1, 2, 3, 4, 5, 6, 7, 8 is going to hang around and do some maths. We can help you with some maths if you've got some other maths you'd like us to do. But by and large, it's me and chat trying to learn what values you can write as the sum of 2 squares or similar. Look at these other problems. This one, if you can work out when this is the number 1, which we're getting close to, we might be there, then you know which numbers are square and also triangular. You're doing real analysis. Oh, good luck. I found that stuff really hard when I did it at university, but probably worth learning in the long run. Good. Okay. Right. Okay. This one obviously represents 2, the only prime that divides that. If your prime divides delta, then you can write. You can make the prime, but you can't make the prime squared. I obviously can make prime squared. Not with a coprime pair. Using the first of the 4 properties, we have this. Wait, what? They've just done this. This is it. This is the calculation. This is the thing we came for. Eisenstein got some. Okay, I'm going to stick with it being Eisenstein and some sort of weird formula for these things. This is the calculation. Here we go. This is going to tell us which primes you can write as the sum of 2 squares. I think, after loads of work across many live streams, here we are. The question is minus 4 a square number modulo p? Which is daft, but here we are. The rule that we haven't proved yet, I suppose, so this isn't totally convincing yet, but the rule is that you can split it apart into these separate terms. You factorise the numerator. Am I going to call it the numerator? It's not really a fraction, it's a Legendre symbol. Anyway, minus 1, 2, 2. And then, right, we don't even have to calculate this because it appears twice. I suppose 4 would be an interesting thing to put out because 4 is a square mod p. So the question is just, is minus 1 a square mod p? Which is something I care about a lot. Is minus 1 a square number? Is a question that seems to come up quite a lot. Is minus 1 a square number? Kind of obviously no, but in some worlds, maybe yes. Same to you. Second property says this is +1 exactly for primes 4. Okay, so it's a thing we've been given in the second property, which is we have this list of properties of these brackets. And I think I called it out at the time that that's the fact. That's the thing that we want to know about. Primes of form 4k plus 1. Primes represented by this are 2, and the ones that are 1 mod 4. But not the ones that are 3 mod 4. If you believe this second property, which we haven't got to yet. So I'll tell us which primes we can make, and then you can make products, and you can definitely make squares if you're allowed to use more things, not pairs that are not co-prime. Go for it. Oh, you can remember that's worth it. It's the sort of thing that hundreds of years ago people would just manipulate infinite series without checking whether they were absolutely conversions or not. Definitely worth knowing. Yeah, because you want to be able to rearrange sums, and the rule is, unfortunately, you can't always do that. Yeah, definitely worth knowing. It means you can get away with stuff that people wanted to do a couple of hundred years ago, but know that you're doing it properly. Otherwise, you run into all sorts of trouble. Yeah, good maths. I found it so hard though. Right, okay. So here's another one. Maybe we care about this one. We care about the discriminant -8. Off you go. And there are several cases to check. Oh my goodness. And it turns out to be these ones. We've seen something like this before. So, if we can prove these properties work, then we can start to grapple with problems we've seen before. Only prime dividing this, which is represented. Yeah, it's got 2 over here. I'm a bit confused. Why are we putting in weird numbers to represent number 2? Oh, I suppose you could transform and rearrange. It's kind of fine. 1 minus 2, but then you've got to look slightly further away to actually find +2. So you've got to look somewhere else. Okay, whatever. For odd primes p, we have this, and there you go, it's these numbers. No -1 in there this time, so none of that. And then one more. 3 is represented. The prime 2 is not represented, because we could check mod 8. And then here we go for the other ones, and there's lots of different cases here. My goodness. Well, it looks like different cases, but then they both work out to be p over 3. So if p is 1 mod 3 or 2 mod 3. And we're starting to see that thinking mod delta is important. Because quadratic reciprocity, when you turn this thing over, you'll see a square mod delta. Whereas previously we've been thinking about delta being a square mod 4n. Quadratic reciprocity lets us flip things around if we're talking about primes that don't divide delta. Starting to string these things together into coherent sentences, which is fun. Right. Yeah, it's sort of annoying maths. It stops a lot of fun. And for catching the chat. Okay. And then 40, 2 and 5 are represented. We know that the primes that divide delta are represented, but then squares of those are not represented. Higher powers of those primes are not represented. For other primes, we know that if you can represent the prime, then you can represent powers of that prime. In the case 2, you have to represent 8, and then you can represent powers from there on. But that's not a thing here because this is even, so we've already talked about 2. You have to keep track of the prime 2. It's a very different prime from the others. Here we are. So the other primes here, they're all odd, so we get to talk about this, where 40 is not impossible. Yeah, anyway, okay. I like this fact that if you see a cube, because you've got 2 cubes up here, you see a cube, well, you only care about the non-square part of this, because all of these Legendre symbols are either 1 or -1. So I quite like that. It looks hard, but then you remember that this thing is either 1 or -1. So when it's cubed, it's just going to give back either 1 or -1. I don't need to actually cube it. Oh my goodness. So this depends on mod 40. interesting. So here's that thing again about it being something about primes modulo the discriminant. We've ended up there. We've kind of recovered a factor of 8, which feels like a coincidence in a way. Because, well, I just said you didn't have to cube, and then we get this term which does involve the cube of 2 to give us back to 8. This depends on primes mod 5, of course. We flipped it over. There might be a plus or minus sign on that flip, but quadratic reciprocity says that there's something to do with the flip. It's got me thinking that maybe I should flip it. If I want to prove this thing about 2, maybe I should be using quadratic reciprocity on that. Or is quadratic reciprocity only for odd primes? Is that why we've got a second property? Down here, have we been told quadratic reciprocity? Yeah, distinct odd primes. Okay, so 2 is different again. Oh dear, prime 2. And then you get exactly 8 of the cases. There's a weird list. Good. Agrees with our earlier observations. Yet to verify our earlier guesses as to which congruence classes represented by which form. That's the next section. But first I would like to prove... running out of time on stream. Where were we going to prove these properties? We've had some examples. Section 6.4? Where are we at? Are we in section 6 point something? Quick look ahead. So I think we're here. Possibly finishing the stream just here. And then what's this? So, we've got some complications to cover other discriminants. Oh, and quite a lot more maths. My goodness, quite a lot more maths. And then a big picture of a quadratic form graph. Nice. More of them. And more propositions. Oh gosh, and then is section 6.4 is so far away. Oh my goodness, I was looking forward to understanding why quadratic reciprocity works. Yet again, there's a whole table of these things. Whole table. Unique representations, so still going. Oh, we're only in section 6.2 at the moment. So we've got all of this before we get to a proof of quadratic reciprocity. And then all of section 6.3, that's a bit disappointing. Oh well, and then genus. So we're going to do sort of 20-30 pages using Legendre symbols before we get a proof that any of this works. I find sometimes this book is relying on doing a lot of stuff before. Maybe the reason why they're doing it. There's so much genus stuff and characters for other ones, and then some exercises, and then hey, Eisenstein's in here. 6.4. There's a rule. Euler's in here as well. So okay. So quick look at quadratic reciprocity stuff. There it is. There's my a to the p minus 1 over 2. Euler's formula. It was Euler, not Eisenstein. Good. Okay. So this is the stuff I was trying to remember. Wilson's theorem, hooray! Love Wilson's theorem. It's kind of a bit funny. Little theorem. Oh, good times. Right, okay. Stuff that I'm going to do. Number theory. Oh no, there's that rectangle again. We've met this rectangle before. It's quite hard to think about. I did not succeed at thinking about it last time. Oh my goodness. Yeah, okay. I guess part of the course for this book that you would have a slightly kind of graphical proof. We're going to prove quadratic reciprocity. They have done a lot of diagrams, bless, which is what was hard about this before. Wilson! Wilson! And then, there we go. And that's section 6.4. Which is then the end of chapter 6, page 213. Whereas we are... So if I want to understand quadratic reciprocity, I have to first get through quite a lot of stuff about characters and genus in section 6.3. I have to finish off section 6.2, which is going to tell me about other discriminants. I've got quite a lot of that, and this table, and quite a lot of this, and all of these charts. So this is going to be a couple of weeks, isn't it? At least a couple of weeks before I see any of this again. Yeah, because it's about 30 pages away. So it's 179. So it's literally 40 pages. No, 21 and 30. Yep. So like 35 pages until we get to chapter 7. So what have we read? I reckon we've read about 3 today. Yeah, because we were here at the start, and we are now just about here at the end. Kind of here. Kind of 4 pages. 180. We go as long as it takes. I think I'm about a month away from that fun stuff on Wilson's theorem and things like that. I'm at 6.9, but it's about 6 o'clock, so I think I'm going to wrap up the stream. Let's quickly have a look at this. Can I quickly look at this? I'm not sure. No, I think I'm not going to quickly look at Bertrand's postulate. I think I'm going to save that for another time. Something. Yeah, save it for another time. I think that's sensible. Prime between n and 2n for any value of n. There's a proof on Wikipedia of that, due to Erdős, that you might know, that uses binomial coefficients, I think. Is this it? So there's Bertrand. Primes between these, less restrictive but neater formula is this. Is this the one where there's a proof? Yeah, using binomial coefficients. See, proof of Bertrand's postulate. Yeah, this is a thing I would like to understand at some point in my life. It's just really cool. So it has this lemma. How does this proof work? Have we looked at this on the stream before? I can't remember, but there's this proof that uses binomial coefficients due to Erdős, which is just so cool. So yeah, so there's this bound on how large the middle term of the binomial coefficients is. Fine, and oh my goodness, there's this: the largest natural number r such that p to the r divides 2 to the n over n. How many times does the prime p go into this number? For any prime p, it can't go in that many times. Here's a form of horrible maths, logarithms, loads of stuff. And then it just keeps going. And it just keeps going. And there's all these hashes. And then it works out. Or something. Oh no, this is just proof of 4 lemmas. And then there's this proof, which then goes even more. And you have to check for the first 426 cases by hand at the end. But you get this kind of like bounds on this thing. So this is kind of nuts. And it kind of feels like I have a chance to understand this if I put in quite a lot of time, but there's quite a lot of learning to do along the way, and I'll get distracted by p-adic order, won't I? So I won't even get there. Good. Driving is okay-ish. I can sort of turn left. In some circumstances, I can turn left. I can't turn right, but 2 wrongs don't make a right, but 3 lefts do. So my plan is to do the old loop round at the moment. If left to my own devices, just haven't got there yet. Just haven't got there. I've learned left first, right in the future. But until then, 3 lefts. Just go round the block. You have to go past, left, left, left. You'll be alright. Good. 270 degrees and all that. Okay, right, good. I'm going to call the stream there, I think. Nice to see you all. Hello to new people in chat, if you've hung around. We'll be back next week. I think I need to make more t-shirts, because this was fun. I've got a maths t-shirt now. It's got Gaussian primes on it, showing their prime factorizations. So I should probably do a write-up for this t-shirt, so that I can link to people to a website, so that if somebody is interested in my t-shirt, I can link them to I can link them to my website to explain what's going on with the t-shirt. It doesn't have the Chill Maths logo on it. I thought about putting it on the sleeves, but then I forgot. So it's just the logo is really just the words Chill Maths in default font. What do they go for on those? A default OBS font, Prima. Is that the logo? Do I want to do one with the fairy diagram on? Kind of do. Oh, you want a mug? Let's find out if I can switch on mugs. I don't think this would work very well on a mug. It's too much. But I would also like to do cat fractal Cat Fractal was only really in one episode, but I think Cat Fractal has captured my heart. Yeah, right, okay. Got to find out if Spreadshirt do mugs. I doubt they do, but got to have a look, right? I like mugs. Topological trousers, right, yeah, okay. Other things are available. Cat Fractal's nice. I'd like Cat Fractal, I think, because then I can talk to people about Pythagoras tree. The idea is that it's t-shirts that have maths on, that you can talk to someone about maths, or just link them to a website to read more about some maths. So that I'm constantly doing maths outreach, constantly, wherever I go. People see the shirt and they're like, I'm thinking about maths now. They might not even realise they're thinking about maths, but what's that shirt? It's maths. And then you can give people like a business card. Find out more about this maths. They do cups, right? Let's find out if we can switch on cups. Cool, right, good. Maybe there'll be a mug command next week. Gosh. The merch. The merch. What am I doing? What am I doing? Right, good. Leaning in. That's what I'm doing. I'm leaning in. It's going to be great. Right. See you all next week. If not on Thursday for professional Matt live stream stuff. Mary is going to come and promote ginger biscuits, I think. Other than that, see you for more Chill Maths. Same time next week. Maybe not my face on a mug. Right. If it is, it's pulling this face. Not sure. Not sure about this mug. Ginger biscuits are fantastic. Look down the camera. Ginger biscuits are the best. Right, there you go. We did it. RFL. In the words of Herb, I'm ending the live stream.